Hi and welcome to the video on revision worksheet 21. So this revision worksheet was based on probability and a little bit of statistics. So there was 4 questions, each 25 mark question, and they came from the DEB 2016 mock, paper 2. It was a section A question, question 4. The 2016 paper again, and this time question 5. So the first 2 questions appeared on the same mock, and then the final 2 questions have come from Educate sample papers. So the first is from paper 2 and the second one is from a paper 3. Both are paper 2 questions and appear on section A. So like I said, 25 mark questions. So question 1. A soft toy manufacturer continuously carries out quality control testing to uncover defects in its products. After testing a large sample of its products, the manufacturer found the probability of a soft toy having poor stitching of 0.03. Now, my advice when doing anything like this would be to highlight any important bits so you tend to come along as you're reading. So this bit is poor stitching is 0.03. And that the soft toy with poor stitching, and that a soft toy with poor stitching had a probability of 0.7 of splitting open. A soft toy without poor stitching had a probability of 0.02 of splitting open. So let's take a look what's actually going on here. We are asked to represent the information on a tree diagram showing clearly the probability associated with each branch. So just to kind of save time, I have pulled this tree diagram up here. So we start with the toy, and each toy has 2 options. It can have good stitching or poor stitching. If it has good stitching, it then has 2 options. It could split open or it may not split open. Same for poor stitching. It will split open or not split open. So let's get filling in our tree diagram. So the first thing they said is that the probability of a soft toy having poor stitching is 0.03. So that's going to come down here where we have the poor stitching branch. Now, what we know about a tree diagram is any branches that come from the same point should all add up to 1, which means that here we have 0.97. So now I have the 2 branches there that add to 1. The next thing that they told us was that a soft toy with poor stitching, so I'm now here, has a probability of 0.7 of splitting open. So we have our 0.7 here. And a soft toy without poor stitching, so that one's here, has a probability of 0.02 of splitting open. So now we can fill in the other side of each of our branches. So this is 0.98 because both of these branches must add up to 1. And here is 0.3 because each of our branches have to add up to 1. Now, what's really important is when you're doing a tree diagram, always put your final probabilities over to the right. So the probability that it was good stitching, so let's call that good, and that it split open is equal to 0.97 by 0.02, and when you multiply that together you get 0.0194. The probability of good stitching and it does not split open is equal to 0.97 by 0.98, and that works out as 0.9506. The probability that there's bad stitching or poor stitching, I should go with the letter P here. So poor stitching and splits open is equal to 0.03 by 0.7, and multiplying that together gives us 0.021. And finally, the probability that there is poor stitching and it does not split open is equal to 0.03 by 0.3, which is equal to 0.09. So we have our 4 probabilities there associated with each of our final outcomes. So just to double check, no, sorry, apologies, I have a typo here already. So it should be 0.009. So just to double check, you want to add all these numbers together. And when you add all those numbers together, they should add up to 1. Because the probability of this whole thing should be 1. And it does, so we know everything has worked out. So the next thing it says, using your tree diagram or otherwise, find the probability that a soft toy chosen has exactly 1 defect. So we have 2 options here. We have, it can have poor stitching. So we come down here. But it only wants 1 defect. So if it has the poor stitching, then we want it not to split open. That's one option. The second option is that it has good stitching. So that is not a defect. But the defect is that actually it's split open. So there are 2 pieces. So we're going to add them 2 together. So the probability of it being good stitching but splits open plus the probability that it has poor stitching and does not split is equal to 0.0194 plus 0.009. And when you add them together, we should get 0.0284, which is, just for our own sakes to keep that in mind, 2.84%. So the next part is the manufacturer has found that the colours used in the soft toys can fade. The probability of this defect occurring is 0.05. So we've just been given another little piece. So the probability of it fading is 0.05. The probability that it does not fade is 0.95 then. Find the probability that the soft toy has none of these 3 defects. Okay, so what's the probability that it has good stitching, that it does not split open, and it does not fade? So if you go to your tree, we want to look on the tree where there is good stitching. So that is 0.97. And there is does not split open, that's 0.98. And now we want to add in that it does not fade, so that's 0.95. So if you listen to the way that we say that, the probability that it has good stitching, and the probability that it does not split open, and the probability that it does not fade. So remember that the and rule in probability is multiplication. So when you multiply all these 3 pieces together, we should get 0.90307. So the next question is, find the probability that the soft toy has exactly 1 of these 3 defects. So exactly 1. So what could happen is, we could have bad stitching. Sorry, I got that right. So poor stitching. So we have a P here. But if it is poor stitching, we do not want it to split open, and we do not want it to fade. The other option is that it could have good stitching and it could split open, but then we don't want it to fade. And the third option is that we want it to have good stitching. It does not split open, but it does fade. So in each of these, what I'll do here, just to make it clear, I will highlight the defects. So here, poor stitching is the defect. Here, it splits open. Here, it fades. So we want to work out the probability for each of those. So what is the probability that we have now? We have the probability that it has poor stitching, it does not split open, and it does not fade. What is the probability that it has good stitching, it splits open, and it does not fade? And what is the probability that it has good stitching, it does not split open, but it does fade? So working through that, so the probability that it has poor stitching only is 0.03. Then that it does not split is 0.3, and that it does not fade is 0.95. Notice that because we've gone with poor stitching, we have to take the S, so the split, and the does not split that's associated with that. If we then take good stitching, so 0.97, the chances of it splitting is 0.02 then. And then the chances of it not fading is 0.95. And the last one again is 0.97 for good stitching. Then we have to look at does not split, so that's 0.98, and then does fade is 0.05. So what these all work out as is 0.00855, 0.01843. Sorry, my fives don't look like fives here. And the last one is, no, apologies. So 0.97 by 0.02, 0.95 should be 0.04753. And the last one then is 0.01843. And we're going to add all of these together to get the total probability of all these scenarios. So you get 0.7451, which is 7.45%. And that's the probability of having one of those defects. I forgot in the last part to write that as a percentage, just for you to get an idea. Sometimes with these, it's a good idea to write them as percentages just to get a sense of it. And we see often in questions that they're asking us what does it mean, or asking us interpretations. And that's a lot easier to do with percentages sometimes because we have a much better sense of the numbers. With decimals, we can get very bogged down in what they actually mean. So it's good practice to turn these into percentages, just for you to have a sense of what's going on. So question 2. Two events A and B are such that the probability of A is 0.33 and the probability of B is 0.45. The probability of A intersection B, so that's an important one, and what that means in probability speaks is the probability of A and B happening is 0.13. Find the probability of A union B, the probability that either A or B occurs. Now, the formula that you have here is for two events that are not mutually exclusive. And these are obviously not mutually exclusive because they have an intersection. Mutually exclusive events do not have an intersection. So the formula we have is the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. Remember that the union means or, so this is like the addition rule, but it's slightly different because we have to take away the intersection. So let's do this, 0.45 minus 0.13. So when you do that, we get 0.65. Now, that formula, where that's coming from, is if we look at this as a Venn diagram. So here's my Venn diagram. I'm going to label this one A and I'm going to label this one B. First thing I always fill in is my intersection. So I have 0.13 here, which means my A is combined as 0.33, which leaves 0.2 for here. And my B is 0.45, so this actually is only 0.32 appears down here. And if I add all that up and take it away from 1, I figure out that 0.35 exists outside. They did not ask us for a Venn diagram, however, Venn diagram is often the easiest way to do these questions. If I wanted to find A union B in my Venn diagram, I would come along and I would say, well, I want everything that's in here and in here. So I'd add all those numbers together. Now, the difference between adding what's in the Venn diagram versus just adding the probability of A and the probability of B that we're given here is that if I add the probability of A, 0.33, and the probability of B, 0.45, effectively what I'm doing is I'm double counting the intersection. And that's why in the formula we have to take away the intersection to stop that double counting. So that's where the formula comes from, and you need to know that formula, so it's worth learning and being able to use it. However, like I said, a lot of times in these questions, the best thing that you can do is actually draw a Venn diagram. It can help really to see it visually, and you'll make the question just a little bit simpler for yourself. So especially for the next part, which is a little bit more complicated, we're going to find the conditional probability that P A complement given B complement. So let's start with just the basic formula for conditional. So the probability of A given B is equal to the probability of A and B happening all over the probability that B happens. Okay, so that is our conditional probability. But notice that here it's not just A and B. I have A complement and B complement. So my formula becomes the intersection between A complement and B complement all over the probability of B complement. Now, what complement means, if we can go back to our sets, I'll just get rid of all that colour here so I can do a bit of work with it. Complement means everything except A. So what I'm going to do is I'm going to take everything that's not A. So the bits that are not A is this and this. And I'm going to find where that intersects with anything that's not B. And the things that are not B is here and here. And you'll notice the thing that I highlighted twice, the thing that appears in both A complement and B complement is this piece here. So that is 0.35. Now, B complement with the two green pieces, so that was 0.2 plus 0.35. So when I work that down, I get 7 over 11, or if you want to turn it to a decimal, 0.6363. Now, state whether the events A and B are independent, justify your answer. So, I forgot to say at this point that the conditional probability formula would need to be learned. So this formula here, you would need to know off by heart. That's your conditional probability formula. The next one that we have is for independence. So how we would prove independence, we would say if the probability of A multiplied by the probability of B gives me the probability of A and B happening, i.e. the intersection, then the events A and B are independent. Okay. So let's check if they are. Probability of A is 0.33. Probability of B is 0.45, and that should equal to 0.13. Now, when we actually work that out, we get 0.1485. 0.1485 equals 0.13. Well, actually, no, it doesn't. Okay. Therefore, A and B are not independent. Okay. And this formula here is another one that you need to learn. And this only works for independent events. If events are not independent, then it won't work. And we often use this formula to prove independence. So event C is such that the probability of C is equal to 0.2. The events A and C are mutually exclusive. Now that's hugely important. So we're basically working, we're basically working with the same diagram we had, but we're adding C into it. Now, we have A, B, and C. And I think people's first thought is to draw like this. Now, if I go back, it says A and C are mutually exclusive and B and C are independent. So we know B and C have an overlap because independence means there is going to be an overlap. However, A and C are mutually exclusive. So if you do it like this, and I work and I call this A, and I call this B, and I call this C, A and C will have no overlap. So this piece here is effectively empty. They are mutually exclusive. There is no overlap. Okay, so that is going to change. So take this out completely, get rid of it. Going back to the original that we had a 0.13 here. We had 0.2, that's not going to change. Now what is different here is we need to figure out what's going to go in here, where B and C intersect. And we know that they're independent, so we're going to use our independence formula. We're going to say, well, the intersection of B and C is equal to the probability of B multiplied by the probability of C, because they're independent. So I know that the probability of B is 0.45. I know that the probability of Z is 0.2, and I know that's going to give me 0.09. So I got a 0.09 in there. Now, there was a 0.32 that was in B, but I'm now taking some of this away. So what I'm left with is 0.23, and what leaves me here is 0.11. Outside, I have 0.24. So that's working through. Having to use the idea of independence here is so important. So now, I want to show you another way that you could have represented the data, which would have made probably a little bit more sense, but was probably harder to see during the question. And it's like this, such that this is A, this is B, and this is C. And the reason you could draw it like this was because A and C are mutually exclusive. They don't touch, so there's no need for them to overlap. Again, this was 0.2, this is 0.13. That didn't change. I've worked out that 0.09 should go here. I got my 0.23 that goes here, my 0.11 that goes here, and outside is 0.24. So really, the second method of the kind of more linear style would be better, but if you didn't see that, as long as you left that A intersection C completely blank, but here I have coloured in to make sure I don't fill anything in, though both are completely acceptable. So the last part then is hence find B union C complement, the probability that neither B nor C happens. So the first thing we're going to do is we're going to highlight B union C. So let me get my highlighter. So this is B union C. And the complement is everything that's not there. So basically I want to deal with everything outside of this. So I'm dealing with these bits here. Okay. So I'm actually looking at so the probability of B union C complement is equal to 0.2 plus 0.24, which is equal to 0.44. Another way that you could have done it is the probability of B union C complement is equal to 1 minus the probability of B union C, which is equal to 1 minus 0.13 plus 0.23 plus 0.09 plus 0.11, and that would also give us the same answer. So both methods absolutely fine, but given that we had the Venn diagram, it would make sense to use it. So question 3, so now we're getting into the sample papers. Often the mocks can be quite tough, and some of the questions are a bit out there, but the sample paper is even more so. So the Bernoulli experiment is a random experiment that satisfies certain conditions. Name any 3 of these conditions. So there are 4 that we have, and they are as such. There are only 2 outcomes. Okay, so the first one is there's 2 outcomes only. Okay, I'm just going to do really high level ones so you're not watching this for ages, but I would expand. So a finite number of trials. So what that means is we don't keep going until something happens. Okay, we're not going to keep going indefinitely. The third thing is that we have the idea of success and failure, and they are fixed, so they don't change per trial, from trial to trial, fixed from trial to trial. And number 4 is that the trials are independent, so one does not affect the next. Okay, so we cannot use this if we do not have independence. Now, just for your own benefit, on page 33 of your log tables, this is where we get our Bernoulli trial. So it's also known as the binomial distribution, and it's given as n, choose or, p to the power of or, q to the power of n minus or, where n is the number of trials and or is the number of successes, and p is the probability of success, q is equal to 1 minus p, and that's it. So that's actually the probability of failure. And when we say success and failure, it's basically the thing we want and the thing we don't. We think of it as success and failure. So the next thing they've asked us is the median annual household income in Ireland is 32,000, and among 10 randomly selected Irish households, find the probability that that 8 or more had incomes exceeding this. So what they basically told us is the middle point of all the data is 32,000, which means that half the data exists above it and half the data exists below it. So therefore, we have the idea that the probability that income is greater than 32,000 is the same as the probability that income is less than 32,000, and they are both equal to a half. So we're basically talking about Bernoulli here. N is the number of trials, so there was 10 people or 10 households selected. P, the probability of success, is a half because we want it now to be exceeding. It doesn't matter because the Q is going to be the same. And they want 8 or more. So or is going to be 8, 9, or 10. So we're going to have to do this 3 times. So we have, using our formula, n, choose or, let's do 8 first. P, a half to the power of, P to the power of or, so that's 8, and q to the power of n minus r, which is 2, plus n, choose or, this time my or is 9, and a half to the power of or, which is 9, and a half to the power of n minus r, which is 1, plus 10, choose 10, a half to the power of 10, and a half to the power of 0. So working through all that piece by piece, we should get 0.055. Again, I'm just doing this for speed, but really what you want to do is you want to show as much work as possible to make sure that if anything does go wrong, that they can see what you are doing. So at least 2 households, so we're trying to find the probability now that at least 2 households had income exceeding this. So at least 2 households. So we basically want to find the probability that 2 plus the probability that 3, or the probability that 4 had it, or the probability that 5, or the probability that 6, probability of 7, this is looking long, plus the probability of 8, plus the probability of 9, plus the probability of 10. That's a lot. But what I could do instead is say, well, actually that's the same as the probability that nobody had it minus the probability that one person had it. So using the idea of exhaustive events, so that all my events there should add up to 1 if it's an exhaustive list. So what I'm going to do is I'm going to do 1 minus. Now, it's going to be n, choose 0. Same exact figures that we had before. This time the only thing that's changed is our or is going to be 0 and 1. So half to the power of 0, half to the power of 10, minus 10, choose 1, half to the power of 1, half to the power of 9. And when you do that, you should work out, again, show as much work as you can, it's just for pure speed, 0.99. So the last question, question 4. The table shows the correlation for 4 graphs below. Match each graph to the correlation. So correlation is generally how the points are looking. So if I put in kind of a line of best fit, so one there, The line will go something like this, and this one will go something like here. Now, not great straight lines. Remember, I haven't got a ruler. But we can now get a sense of which graph will be which. So graph A is definitely positive. So we look, the line is going up. And if you compare it, it's actually not as strong as C. Or sorry, C is not as strong as A. So A is a bit steeper. So the correlation is looking a bit stronger. So graph C is looking a bit flatter. So that would give this one as C and this one as A. B and D are both negative, but B looks stronger. So B would go here and D would go here. Again, D is that little bit flatter. So then this was a bit of a strange question, but it's good to see it. So standard normal curve is shown for the probability distribution of a random variable z. Z1 is the value of z on the horizontal axis. Use your curve to locate z1. So what we want to do, again, remember I'm not using a ruler. So you want to go straight across and come down, and the point here that we identify that mirrors the same height as Z1 is minus Z1. And it says shade in the region representing Z is greater than Z1, so that's this part here, and Z is less than minus Z1, which is that bit here. And is Z greater than Z1 equal to Z less than Z minus Z1? And yes, because there's symmetry within this normal distribution. So what's the probability of 0? So what's the probability of that single piece, that single line? So it's the area under the curve. So it doesn't have an area because it's a straight line, so it is 0. What's the probability that z is between minus infinity and infinity? So that's going to include everything. So the biggest probability that we can have is 1. Remember, all probabilities are between 0 and 1. What is the relationship between the probability that z is greater than z1 and z is less than or equal to z1? Okay, so what we have is the probability that z is greater than z1. Okay, so this piece up here, so z is greater than z1, is equal to 1 minus the probability that z is less than or equal to z1. So we're looking at, and I'll just highlight in a different color, where z is less than z1. So all of this piece back here. So basically the bit I've highlighted in yellow plus the bit that there to the right in blue will all add up to 1. The last part then, what's the probability that z is greater than 0? So that's 0.5. And what's the probability that it's less than 0? 0.5. So half of the probability, or half the area, lies to the left and half it lies to the right. So if we include the 0, does that change anything? Well, no, it doesn't, because it's still 0.5 and 0.5. It's a little bit of a strange question, but it's good to kind of test them, but revise the basics of it.